There we
Thank
go.
you.
So yeah, I moved to the UK in 2023, was a postdoctoral fellow at Imperial, and then now I've transitioned into a full research fellow at Imperial College doing broadly climate research. And I'm actually coming to you, I'm on a brief sabbatical in Cambridge. So I'm really enjoying seeing another part of the UK. Um, yeah, getting used to it's a very different climate than Boston, more different than I suspected. So it's been very interesting. Anyway, so what I'm hoping to achieve today is to give you all essentially I took my introductory geophysical fluid dynamics class and I've made it into a primer and hopefully given you the content relevant to specifically the UK because I realized a lot of my previous content was specific to North America and that's not quite right for this audience. Um, and then I kind of if you have questions, my specialty is mostly in climate modeling and climate prediction. So I will do my best to answer questions. And if I don't know, I'll point you in the right direction. But specifically, if you have modeling questions or questions about how climate models work or what the cutting edge is, I'm happy to chat about that. Um, but yeah, so I'll get into it. Let me see if I can share my PowerPoint.
So while Colleen's doing that, if you keep all the questions until the end, please. Perhaps pop them in the chat if you wanted to. Um, and keep your microphones on mute, please.
All right. Okay, so I'll get started. So, a brief overview of climate dynamics and how we try to predict changes. I'm going to walk you through very briefly, like basics of Earth's atmospheric structure, which you might already know, but it's never too much to review. Um, the kind of tropospheric circulation, which is where we inhabit this tropospheric layer, the lower layer of Earth's atmosphere. The stratospheric circulation, which is actually quite different and very interesting. And how those two things kind of work together to form these really quite interesting patterns of variability that specifically impact the UK quite a bit. Um, and now, in order to understand future predictions, we have to be able to model those things in some way. And so I've got a little bit of information on how climate modeling goes about doing this and how we start predicting climate in future. And then I've looked a bit at what the specific predictions and projections are for change in the UK that we could expect um, based on different kind of pathways that we might end up on. And then hopefully I've left enough time for questions and discussion. Um, yeah, so with that, I'll kick us off into the basics. Um, which to be fair, I think when I started my PhD, I don't think I could have told you a lot of this. Um, so what I've shown here is just a figure that describes how on the left-hand side, you'll see how temperature changes with altitude. And as you can imagine, it gets colder as you go up higher. Or excuse me, how pressure changes with altitude. It gets less dense as you go up higher in the atmosphere. And then on the right-hand side, we see this delineation. We see in the troposphere, temperature gets colder as you go up in altitude, and then you hit this inflection point between the troposphere and the stratosphere. And then you actually start to warm up quite a bit as you go up higher. And actually, the reason that we see this, what we call a temperature inversion, where you go from a decreasing temperature to an increasing temperature, is actually because of ozone. So the ozone layer that's in the stratosphere that we historically had a hole in and continue to sometimes have a hole in, ozone particles actually absorb energy from the sun and they vibrate and create a layer of heating in their local vicinity. And that actually heats up the air enough in the stratosphere to cause this temperature inversion. And that ends up being quite important for describing all of Earth's circulation. And once you kind of pass by, the ozone layer is relatively constrained to between like 30 and 40 kilometers. You start to see the temperature decrease again, and you're in the mesosphere at that point. And to be completely honest with you, I don't really deal with the mesosphere very much. I know very little about it, and essentially so little of the mass of our atmosphere is up there um, that it certainly has an impact, but it's quite less studied, but could prove important in the future. I don't know. That's a ripe area for future research. But those are kind of the basics, and I'll kind of come back to this general scheme as we continue. Um, Now, the atmospheric circulation, you can really just think about it from the perspective of understanding buoyancy. So Atmospheric circulation is a large-scale motion of air, which, together with the ocean circulation, is responsible for taking thermal energy from the tropics to the high latitudes and ultimately trying to balance out this incoming energy we get from the sun and the outgoing energy we get. So if you were to think of the most kind of basic conceptual energy balance of the Earth, you would have, okay, the Earth is some blob. It is absorbing some amount of the heat that it's seeing from the sun, and the rest of it must be going out to space. And those three things must be in balance. Incoming must equal outgoing plus the amount of temperature adjustment you have at the surface. So from that kind of very basic perspective, you can kind of think of it as a bit of a little box model. Um, Now, when we think about the actual motion of air in the atmosphere, you get this motion because you have uneven heating of Earth's surface, where you've got much more heating happening in the tropics and much less in the poles, and that varies seasonally. Um, so, the other basic concept, if you have uneven heating, um, if you have a warmer air parcel, it is less dense, meaning it how typically will want to rise in comparison with a colder, more dense air parcel. So these kind of two concepts together can get you most of the way to trying to kind of logically sort out the tropospheric circulation, that circulation in Earth's lower part of the atmosphere. And so if you were to take that logic and apply it, you say, okay, I get more the sun's energy at the surface in the tropics, so at the equator, you would expect, or I would expect, air would rise at the tropics, and then, okay, it's cooling, and it would flow towards higher latitudes and then flow back to the tropics, heat up, and you'd have this convective cycle. Kind of like what you'd expect if you had a big pot on a oven and you're heating the bottom in one place and you aren't heating the outside. You'd expect to get this kind of convective cell. And so if the Earth wasn't spinning, you also expect things to kind of stay in a straight line. Now, if we expand this one cell model to including Earth's spinning effect, the Coriolis effect, as the air comes back towards the equator, it's actually kind of pushed to the left. And so you end up, well, to its right, to my visual left. I always get that confused. That's the right-hand rule with physics, which I fully did not learn. However, you kind of end up with this motion where things at the equator are flowing from east to west as air comes back at the surface. And that's actually quite interesting in the context of historical like sailing routes. People would take advantage of these like typical wind patterns to travel across the Atlantic Ocean to the New World, as they say. So now the reality is we don't have just one cell that's part of the circulation. And it's quite interesting that we in fact have three cells. Um, Now, this has a lot to do with the total amount of energy received in the tropics and how far northward that air parcel can travel before it sinks and travels back towards the equator. And you have to have a relatively strong temperature gradient between these two locations to kind of maintain these cells. But the reality is we have these three cells. So the first cell is called the Hadley cell. And basically it takes very warm, moist parcels of air in the tropics, because that's where you've got large amount of kind of ocean coverage. You have this rising wet air, and as it rises, you can essentially imagine the atmosphere freeze drying that air out. So you end up getting all this precipitation coming out. The air is less likely to hold water, and so this range, I think you can maybe see my cursor here. This area is called the intertropical convergence zone. So this region where these air parcels, this warm, moist air is rising, losing its moisture, and then kind of moving northward and then descending again, is gonna be where you get these strong rainfall bands. And so if you look around the globe, like this is right about, and this has kind of a north-south traverse because the sun's shining slightly differently around the equator as a function of season. That's where you're going to get a lot of rainforests. You're going to see the Amazon rainforest is very much impacted by the ITCZ. Additionally, at the kind of top end of this cell, um, are regions that are really maybe on the edge of being wet or dry. So if I know in the Sahelian droughts in kind of this mid-northern part of Africa, it's the northernmost extent of the ITCZ's traverse. So the ITCZ will traverse north-south as a function of season, and that region just happens to be right on the edge of the northern traverse. And so if for some reason during that season it doesn't reach the Sahel, it doesn't get rain. That rainfall just doesn't reach that area. And that prolonged changes to that traverse end up dictating droughts. And that region is particularly susceptible from a food security perspective. So that's just an interesting tidbit. So that's kind of the Hadley cell. So this is easily described as kind of a thermally driven cell. And you get a very similar thermally driven cell at the pole, this polar cell. So cell number three, where you've got warmer air kind of at like 60-ish degrees north, so quite far north, that rises, cools, and then sinks and creates this, um, I don't know, thermal cell. And it took me a very long time to understand, well, then how the heck are we getting, how the heck are we getting this middle cell? Why is that moving? And you can kind of imagine it's like the two cells around it are actually driving it. So it's almost like that air is just being pushed like a gear between two other gears that are going around. And because of that frictional force and these kind of eddy turbulent forces, you end up creating a kind of mechanically driven cell there, which is quite cool. Um, so that actually for quite a long time historically was not necessarily the most well understood piece of the circulation system. And understandably so, because it's not particularly like for me intuitive. So yeah, so they call the thermally direct cells, meaning you have hot air that's rising, moving, sinking, the Hadley and the polar cell. They directly are moving thermal energy into kinetic energy. And then you've got the thermally indirect cell, that middle cell is the ferrule cell, where you have colder air rising and warmer air sinking in a way that seems quite odd, but it's all possible because you've got this eddy, turbulent driving force, so mechanical force. Um, and this is particularly interesting because this tends to steer where the weather in Europe and North America kind of is happening. So the storm tracks. And in particular, if I go back here, the region where the polar cell and the ferrule cell kind of abut each other um, leads to what we call the polar jet. So this region is where you've got a lot of different kind of air masses colliding and you generate a region of strong winds, which I'll get into a little bit later. Well, right here. So the polar jet stream, which is something that is really impacting the UK, um, sits at about 9 to 12 kilometers and about 60 degrees north. So it's quite far north. And specifically in the wintertime, when the kind of equator to pole temperature gradient is quite strong in the stratosphere, which I can get into a bit later, the speeds of this jet stream go up to 300 kilometers per hour. So you've often probably noticed that, like, well, I've noticed recently, I've obviously been flying to see my family in Boston. It takes a lot longer to go from the UK to North America than from North America to the UK because what will happen is if you're flying, especially in the right place, you end up kind of in this jet stream, and you're pushed around, like pushed quite a bit faster. Now, that jet stream will dictate where regions of rain, um, storms are happening. So if there's a year where that jet happens to be sitting quite squarely over the UK, that's typically a year of increased storminess. Um, Now, the reason that it moves and it's not just completely stationary in one spot is because you've got things called waves, Rossby waves, um, that end up making that jet stream wiggle. So if you kind of think of the atmosphere as an ocean of air, you have disturbances in the air that cause wave structures, just like you'd see in the ocean. And so if I have a wave that ripples over what I would say is like almost like a ribbon, that ribbon will wobble. And if it wobbles northward, it'll bring this kind of warmer tropical air. over the UK. And if it wiggles southward, it'll bring this cold Arctic air over the UK. So even in the US, we've had situations where the kind of that polar jet dips so far south that it brings really cold Arctic air in places where you really wouldn't typically expect to have really, really cold temperatures. Um, we'll get in a little bit to the vortex, which is actually sits a little bit above the jet. Um, but hopefully, I wonder how much this has probably come up in the news when people say, oh, we've got like a vortex outbreak, you've got a cold air outbreak, and this is the mechanism through which that is really happening. There's also a subtropical jet stream, which sits between your other two cells, between your Hadley cell and your Farrell cell, and that's about 30 degrees. Um, it's more consistent. It's less impacted by wave breaking or wave ripples that flow through our atmosphere. And that typically influences monsoon systems and cyclone paths, and it firmly separates both of those cells aloft. Um, and again, this is also a place where airline pilots can predict or try to predict where that is and fly in that region of higher winds. And I know right now there's a lot of people using AI models to try and better predict where pilots can fly so that they fly the most optimally efficiently through these jets to take advantage of the wind patterns. Let me just okay. So that's yeah, here's kind of an image. This was from the Met Office, showing the wind speed. Obviously, you can kind of see this meandering pattern of the polar jet, and it's obviously wobbling. And you would take it to mean that the air that's sitting northward is quite cold, and it's separating a region of much warmer air further south. And its behavior over, obviously, right here, it's directly over the UK, meaning you're probably getting quite a bit of rain and a bit of windiness and storms. So now, in the context of climate change, obviously, we can understand the case that the UK is quite impacted by the position of the jet. In When we think of climate change, I think people have probably thrown around the term Arctic amplification, meaning the Arctic areas are warming faster than other parts of the Earth. So that means that instead of maintaining the temperature difference between the tropics and the poles warming faster. So the temperature gradient is getting less. The temperature difference from the tropic to the pole is diminishing. And that means you get a weaker polar jet. So the weaker polar jet is more susceptible to wobbles or waves in the system, and it will tend to wobble more. And we have this less stable separation of Arctic air and more southern tropical air. So the assumption is that you'd have more variability in temperatures with climate change, somewhere like the UK, because you're going to start to see increased wobbles in this jet stream, bringing either cold air outbreaks or warmer southern air. Um, what's interesting in the context of modeling this is that there's such, it's very difficult to capture the historical observations of the jet, such that we don't have, I think, the most robust ability to predict future changes. So while there's a basic mechanistic understanding of what would happen, quantifying where the jet might more typically lie or what the wigglier jet might look like is actually quite difficult. Um, and part of that has to do with other parts of the Earth system that affect the jet, which I'll get into next. So the stratosphere is actually has quite a big impact on the strength and wobbliness of the polar jet, as does the equator to pole temperature change. So, a brief intro to the stratospheric circulation. So, I'm going to go back to this plot. So, we've just talked about the tropospheric circulation, which is this more turbulent region where all weather is happening. It's where we live. Um, and it is, I think, where people are focused at looking for climate change because that's where all of the surface impacts will occur. Um, so only in the past decade or so has there been a recognition of the importance of including the stratosphere in climate modeling in order to actually fully capture surface climate. So the stratosphere, again, it gets warmer as you go up in height, meaning it doesn't have the same convective overturning um, dynamical system happening because you have colder, denser air at the bottom. So it doesn't want to rise compared to the air above it. The air above it is warmer. And so for a long time, people assumed that the stratosphere was stationary, and that it wouldn't necessarily have a circulation. And what happened was people were detecting levels of water vapor that were extremely low. It was extremely dry. And the assumption was, okay, well, how is water vapor moving from the tropics to higher latitudes? The higher latitudes are much drier. So then this kind of prompted the assumption that, oh, we must be able to move material in the stratosphere from the tropics to the towards the poles. But what would be the mechanism? And it turns out that the stratosphere is actually a wave-driven circulation, meaning you have it, it is in radiative equilibrium, and there are waves breaking in the stratosphere that push it away from radiative equilibrium and move material, mechanically move material from the equator to the pole, which is really quite cool. In fact, they even call this kind of tropical region here the um, like the surf zone. So you can really imagine this being like an ocean with waves crashing, which in 3 dimensions is a little bit challenging. I'm used to looking at like the actual ocean where I can imagine a plane and a wave crashing. But you have momentum deposited when a wave breaks and it kind of pushes material. Um, there is a role for the mesosphere here, which I won't really get into, but it kind of modifies gravity wave breaking, which is a different type of wave. You've got smaller Rossby waves, which are often sometimes called planetary waves, and that is moving material and mixing it around. Now, the stratosphere, because air isn't necessarily rising as a function of the temperature, um, it has a really interesting way in which material gets into the stratosphere. So, one of the biggest sources of material, like small particles called sulfate aerosols, are put into the stratosphere by volcanic eruptions, where it's literally like the explosive energy of the volcano pushes material up into the stratosphere. And once it's there, this kind of wave-driven circulation moves it throughout the entire stratosphere. So it's a single cell system, so it's quite good at moving material from the tropics to the poles. It does take about 2 years. So it's like relatively slow. Once material is there, it's going to maintain or be retained for quite some time. Um, the only real, I guess, the way in which we currently understand that water vapor gets into the stratosphere is that in the tropics, where you have all that warm, moist air that's rising, it'll rise, it'll often um, rise up through the kind of, temperature. It's decreasing in temperature as it's rising. Essentially, it's being freeze dried out. And whatever water makes it into the stratosphere, that's kind of what's setting the water vapor budget for the whole stratosphere. Um, there's an increasing kind of concept in the atmospheric community that you also get like convective overshoot. So if you have a really strong thunderstorm, that basically has so much energy and you have such like the air parcels themselves want are like so out of balance with the air around them that often they'll overshoot into the stratosphere, inject water, and then come back down. And people are like currently doing research to try and quantify how much water vapor might be entering the stratosphere through that pathway. But I think it's quite interesting. It's relatively unknown. It's hard to quantify. We have some measurements, but historically, we definitely have measurements of the stratosphere. We have kind of an idea of the temperature. We have an idea of kind of how much water vapor is there. And there was obviously an interest in understanding the ozone layer um, once we discovered that there was an ozone hole. But because of that, there wasn't interest before then. So we have relatively short observational time series of these constituents. So I think the stratosphere is something that researchers are have been investing in and are now really starting to understand. Um, so one of the key features of the stratosphere is what we call the stratospheric polar vortex, which is almost like the stratospheric sister to the polar jet stream that we were looking at before. So while we like to delineate areas in the atmosphere, like it is one mass of air. And so what you have is you have a vortex, a strong polar vortex, and this is the wintertime vortex in polar night, that sits above what is below it, the polar jet stream. And so I guess this image on the left is trying to kind of show you that 3D um, vertical structure. Um, and what's quite interesting is that you can get these disruptions to the vortex, which are again wave driven. So if you have some sort of um, really large disruption that rises into the stratosphere and disrupts, you can literally break the vortex into two chunks. I always kind of in my mind, I'm always imagining like a water tank where I've got a vortex, but if I like kind of shake it enough, I can probably break that into two spinning bits. Um, Once you break down the vortex, that actually kind of cascades down into the troposphere and can disrupt the jet stream as well. And so I don't know, this might be more North America oriented, but in 2021, there was a sudden stratospheric warming. We call these sudden stratospheric warmings because when you disrupt in this way, you actually get a really massive temperature change in the stratosphere, which should be quite cold. It becomes really warm before it comes back into equilibrium. Um, but it basically pushed the polar jet so far south it was over Texas, and you had this kind of it was called the Texas freeze, um, and it was an insane event in the U.S. You had people in Austin, Texas, with their toilets freezing. You know, the city was obviously not prepared for this type of weather anomaly. It had, I think, millions of dollars of agricultural damage. And it's something that's really hard for scientists to predict. So people didn't have a ton of time to prepare. So when we do kind of future predictions to understand how extreme events might change, understanding changes to the stratospheric polar vortex and the polar jet stream is a huge area of research to try and understand, okay, do we expect there to be more of these disruptions because of changes to the structure? Um, does that translate to more extreme events at the surface, like these, freezing events, which would impact also places like the UK in the same way, which I feel like the UK is prepared a little bit in both directions. You kind of can handle a little bit warm and a little bit cold, but maybe not a lot warm or a lot cold. That's only my personal finding from my apartment in London, which doesn't seem to be insulated. So, but this is really something to consider. I guess if you want to go off and do your own research, I find this to be really interesting, and the kind of mechanics of how these things break down is quite cool. But I won't get into it here. Um, Now, there's also these kind of related patterns of atmospheric variability. So you obviously have the kind of general circulation, which is kind of ever ongoing. Um, and we kind of have a relatively okay idea of what that should look like, and it varies seasonally. And then you've got what I will call these patterns of atmospheric variability. So these are recurring large-scale shifts in pressure and circulation that dictate regional weather and climate on the order of weeks to decades. And so I think probably the most famous is the El Niño Southern Oscillation, which is an oscillatory climate feature, and its kind of counterpart is the La Niña Oscillation. And then most relevant to the UK would be the North Atlantic Oscillation. And then you have a very similar pattern in the Southern Hemisphere called the Southern Annular Mode. And these modify regional and global temperature, precipitation, and storm tracks. In particular, I'll focus on the North Atlantic Oscillation, as I think it's probably most relevant. Let me see if I can go. Okay. Here we go. So the North Atlantic Oscillation, I think when I first started studying this, I thought this looked, people, I was kind of like, is this a pattern? Is this just kind of a blob map? But what we see, this is the kind of temperature pattern describing on the left-hand side the negative phase of the NAO and the positive phase of the NAO. And we see that during the negative phase, you have this positive temperature anomaly over kind of northern North America and Canada, as well as Greenland. And here's the UK. You've got a kind of negative temperature anomaly over the UK. And in the positive phase, you have sort of the inverse. So you've got now a cold anomaly over northern North America, and you've got a warm anomaly over the UK. Um, the way that this was described to me in my classes was actually from like an air mass perspective. And the idea is that there's kind of what they describe the plunger theory. If you were to put a toilet plunger on the top of the Earth at the North Pole and you'd push air mass south and it would flow so that you have less air over the North Pole, more, probably south of 30 north. And if you pull up, you pull mass back up and over. And people have described the NAO as basically a plunger of air. So you have a mass of air sloshing northward and then sloshing southward, sloshing northward and southward. And that change in pressure ends up dictating these differences in both sea level pressure as well as these temperature patterns that we now know are indicative of that particular oscillation pattern. Now, during the positive phase, um, you've got let me go back. The way in which this was historically measured was basically on two islands. They had these meteorological stations, and they noticed there was this consistent change in the difference in the sea level pressure between those two locations. And that is now referred to as the NAO index. It is feels quite arbitrary. So when they refer to the increased difference in pressure, is literally these kind of two box regions. You measure the pressure in both of those regions, you take the difference, and then you can start to see, is that pressure higher or lower than average? Does that mean I'm in the positive or negative NAO phase? Now, in the NAO phase where the pressure is higher, meaning you've got more air mass sitting over the North Pole, the jet stream is shifted north, which you can kind of imagine, right? Like if I'm sucking mass upward, then I'm moving that jet stream north and I'm moving all this air northward and I'm moving the storm track that comes along with that jet stream. And Europe then experiences more storminess and precipitation, and it typically is warmer than average because you're moving air from the lower latitudes up. During the negative phase, when you're basically pushing that plunger down, air is pushed down. The jet stream and storm track have a more west to east orientation, and you've got decreased storminess, less precipitation, but it's a bit colder in Northern Europe. So you've got these like colder, drier, or warmer, wetter kind of patterns to each phase. And my understanding is if you go on the kind of the Met Office will often tell you, okay, this next 6 month period, we're in a positive phase. You can expect, either a colder, drier situation, which I think I've come to like a little more than the warmer, wetter storms that have come through. So that is, I think, quite, I guess, in my experience, the NAO wasn't something I learned about in school. It wasn't something I learned about at university, but it turns out it has quite a big impact on our everyday weather, especially in North America and the UK. Now, what I'll spend kind of the most time talking about, because this is my field of research, is how we go about building climate models and predicting future climate change. I don't have a ton of slides, so I'm hoping to kind of just have more of a discussion and move through things slowly. So hopefully you can walk away and feel like you can, you know, do your own research if you want to, or, interpret the IPCC report with confidence. So climate modeling community has kind of a hierarchy of models that it will use. And oftentimes, if you are trying to say, due to an increased amount of greenhouse gas, I expect there to be some amount of change. You often need to be able to back that claim up with a mechanism describing why that change would take place. And to do that, you often need to use really complex models coupled with much simpler idealized models so that you can simplify out the processes that matter to your claim. So at the bottom of this pyramid, we have the kind of least complex model, this energy balance model. The energy balance model is essentially the simplest version, is what I told you, where I assume the energy from the sun is balanced by the total temperature change at the surface of the earth, plus the energy out. So as long as you kind of have energy balanced and you've calculated how much of that energy is being transferred to mass and matter in the Earth system and how much is being lost to space, you should be able to broadly calculate what the temperature change is if you understand the heat capacity of the medium. So these are quite nice to do, for example, like a lot of like planetary scientists will use this type of model to roughly estimate like it's often called the skin temperature of the Earth. That would be the temperature if there wasn't an atmosphere. You could do that for other planetary bodies. If you don't know what the atmosphere is made of, if you maybe only have a rough guess of what the kind of surface is made of. Um, so that's kind of the simplest place you can start. Uh, the radiative convective models, these start to combine um, the movement of mass and energy through a system. So radiative convective models often will be, like one example is if you take a column through the atmosphere and you say, okay, I'm going to divide that column into, discrete layers. So say I decide my atmosphere, I'm going to describe that by just saying I have three layers in my hypothetical atmosphere. And I know how much energy is coming from the sun, and I know how much my surface is heated up. And then the outgoing energy has to move through my three-layer atmosphere. What I can do is start to calculate, okay, how much energy would this layer absorb? And that would be dependent on the composition. So say I'm moving through um, a layer of ozone, which absorbs a lot of energy and creates a lot of heat. I would lose less energy. Um, excuse me. I would emit more energy. I would increase that temperature layer. I'm getting too deep in this, but you can basically do these really simple line by line atmospheric models that give you a better sense of how the temperature is changing through space. Um, This can be 1D, this can also be 2D. It depends on kind of what you're doing. People have done what they call linearized models, where they take these kind of systems of differential equations and try to linearize them out so you can solve them more quickly. Because the thing that you run into with climate modeling is actually like compute power. It either takes you and your pencil and paper a very long time to do these calculations, or it takes a computer quite a long time to do some of these calculations. And so by doing a simpler model, you can save time, but you give up complexity. Um, as we move up, the atmosphere and ocean GCMs, which is a global climate model, um, those are typically fully descriptive models of a given part of the Earth system. So either the atmosphere is fully described or the ocean is fully described. And then when you go up, you kind of have coupled versions of that. So if I have the atmosphere ocean global climate model, that means I'm representing the kind of full atmosphere and a full ocean, but maybe I don't have something like the sea ice represented, and maybe I don't have river runoff represented. And then kind of these fully coupled Earth system models are like the creme de la creme, the most complex versions that we have. Those will have, they'll represent the full atmosphere, the full ocean. They usually have a vegetation model, a land systems model. They have river runoff, they have sea ice, land ice. Um, they're incredibly complicated, but they're also incredibly expensive to run. And so oftentimes, especially when you're testing, new mathematics, you're going to go down to the simplest version that you can run to do testing and then build complexity. Um, I know a personal anecdote. At the moment, I'm working with the Met Office to update a mathematical representation in the UK Earth system model. So that's the fully coupled UK model that is housed at the Met Office. That is a really, really good model. UKSM and the Community Earth System model, CESM, are regarded as two of the best models. And we basically changed one small parameterization that was describing how clouds behave um, on like a particle level. So we were saying, okay, we actually think that the cloud condensation nuclei might behave slightly differently. Let's update this. And we ended up with a climate that was totally different than what we started with. And so basically, we ended up having to scrap that, go back to this individual atmosphere model, figure out, okay, why did this change our radiative balance so much? Why did this modify how energy is moving through the system so much? Recalibrate everything, and then go back through the kind of complexity pyramid back to the top. And instead of being like a very short, fun project, it was like a 3-year long project. So these things can be, I guess, a little bit more sensitive than expected sometimes. Um, what I think a lot of people spend time on, especially in something like the Met Office, when you've got a fully developed Earth system model, is basically integrating new observations. So as more and more observations become available, there has been a move to, instead of calculating from physics equations, um, instead of calculating certain features, you could use a statistical model, which is like a machine learning model, to just compute relationships. Now, there's a lot of criticism of this saying if we are in a situation where CO2, we're moving into a kind of new regime of CO2 forcing, which hasn't been represented in the observations historically, like is it even possible to apply a statistically learned model to an out of sample situation? And I think that's one of the main points of discussion in the climate community right now. Like, is there a way to help us gain computational efficiency without sacrificing predictive capacity? Um, where can these things fit in? Where can they not fit in? Where should they be used? How should they be understood? I think that's like a real point of the discourse right now. Um, okay, so coming back. GCMs, or these like fully coupled models, as I've said, they discretize the atmosphere into a 3D grid or oftentimes sometimes like a hyper complicated grid. But they solve equations of fluid motion, thermodynamics, and radiative transfer at each grid cell or across each grid boundary. And they can simulate realistic weather patterns, jet streams, um, the complaint about GCMs is sometimes that they don't do a very good job. But what I would say is that I think all models are useful and they help us learn. Whether or not models are capable of helping us perfectly predict the future, now that's up for debate. But I think that they're certainly able to tell us that greenhouse gas, emission has driven warming and changes to the climate without a doubt. Um, Understanding exactly how changes will occur, it requires more and more work to get more and more kind of niche and regional knowledge. Um, and it's very system specific. So that said, I think it's a pretty incredible thing that we've been able to build these massive models. In particular, one area of research now, this kind of parameterization section, any process that can't be described because it exists on a scale too small or much smaller than the grid scale at which the model itself runs, has to be parameterized, meaning it's kind of every time step, there's some kind of empirical equation that's telling you, okay, here's what this thing is doing, and here's how it feeds into your bigger spatial domain. Um, a lot of these parameterizations, this is kind of the area where people are thinking that machine learning or statistical relationships can replace some of these traditional parameterized functions, because these tend to get pretty clunky. Because they're so clunky, you often have to choose which process is most important to you instead of being able to represent them all. So if I had a faster way of doing this, then I could include more important processes and maintain my computational tractability. One area where this is most important in particular is aerosol cloud interactions. So aerosols are like any small particle that stays aloft in the air. Um, Dust, sea salt spray, um, pollen. You've also got black carbon, these other kind of particulates that are in our atmosphere. They interact with clouds in really, really complex ways. And because clouds can reflect incoming radiation or lead to local warming, they have a massive impact on how sensitive the Earth system is to a change in carbon dioxide forcings, CO2 forcing. And so this kind of cloud aerosol interactions is, I would say, the maybe the most pressing area of climate research in the modeling community at present, if I'm thinking in the atmospheric realm. The ocean circulation, I know, is still quite um, difficult. I know I typically, to simplify my models, use what we call a slab ocean. So instead of fully resolving the circulation of the ocean and the energy uptake of the ocean, you basically say, okay, I'm going to treat my ocean like a heat sink. Because what models do that are in the IPCC report, et cetera, they end up having to run for such a long time because it takes so long for the ocean to equilibrate the surface temperature because it is functioning on such long timescales and taking up so much heat. Um, so it depends on your objectives. I'm studying really small scale processes, and so I don't necessarily need the ocean to equilibrate. I need to have a realistic image of the heat flux. Whereas if you are doing an IPCC report and you really want to understand climate sensitivity, then you need to have the full ocean attached and you need to run it until you hit equilibrium. Anyway, so I'm just going to give you a couple examples of Earth system models. I had mentioned CESM, and then on the next slide, I have UKSM, are some of the two most prominent big climate models. CESM is housed at the National Center for Atmospheric Research in the United States, in Colorado. Unfortunately, to my knowledge, at present, Trump is actively trying to sell off parts of it, which it's hard to understand why you would want to do that. I think it's one of the most prominent, places for climate research. And this model is community-based, it's open source. Anyone can download, and I mean, I guess not anyone, there's quite a large amount of capacity to run something like this. But you could download on your own computer a subset of this, and there's community support. They have a help desk, they have a help bulletin. So I know my dad downloaded the atmospheric column model from CESM, and he was able to just, as a normal, non-scientist, play around with it with support, which I think is really valuable to have that level of support. UKSM is obviously the Met Office model. It's also like extremely well maintained and extremely well documented and kept up. And it has obviously this model atmosphere. You've got a glow map, which, as far as I know, is a really top of the line aerosol and chemistry module. So I think a lot of models have sacrificed some of the atmospheric chemistry because it's so complicated and it requires so much compute. UKSM does have this integrated. It's got sea ice, ocean physics, marine biogeochemistry, which is, I mean, kind of wild that we can even get to that level of detail. I know it specifically does like glacier representation and ice sheet representation, Greenland and Antarctica. And then it's got land physics, biogeochemistry, and dynamic vegetation. So dynamic vegetation, for example, enables, as we increase CO2, the behavior of plants will change and the respiration um, and kind of photosynthesis and how agriculture will change. So modules like this enable downstream impacts assessment for example, agricultural outcomes. So people will often take outputs of models like UKSM that do have dynamic vegetation, take key parameters, and then feed them into impacts assessment models or agricultural models to say, okay, under these future scenario conditions, I expect that, soy will behave like this, corn or maize products will behave like this. Um, and so having this all integrated is incredibly useful as we look at downstream impacts. Now, thinking specifically about future projections and changes in the UK, um, I'm imagining what you've probably already seen this and talked about this, the different RCP scenarios. Um, I know right now CMIP 7, so the IPCC report and CMIP 7 are coming out. So this is the new phase and the new kind of backgrounds emissions scenarios. Um, for CMIP 6, we had, I guess it's even older than this, might have been CMIP 5. Um, but you typically will have a low emissions scenario, a medium emissions scenario, and a high emissions scenario. Here, RCP 8.5 was historically called this business as usual scenario where we don't cut emissions. And you typically see, here they're estimating about 5 degrees Celsius global average surface warming, which would be catastrophic. Um, I know, as far as I know, the new IPCC report will include really different scenarios. There's one incredibly, I would say, enthusiastic and optimistic scenario where you have um, a bit of temperature overshoot, but we're aggressively cutting emissions and then have negative emissions by about, what, 2085. There's more of a medium scenario where there are emissions cuts, but you still have a temperature increase. And then we also have what is now known as an updated business as usual, which is dictated by updated information about our current emissions. Um, Now, based on these projection scenarios, people will take the emissions from the RCP scenarios, which these actually feed out, CO2 emissions, but also they feed out greenhouse gas emissions such as methane, nitrous oxide, um, CFCs. They also dictate your aerosol emissions. So aerosols are another kind of just really interesting thing. One of the big aerosols that gets emitted is SO2, and it's emitted when you burn fossil fuels, specifically coal power plants and smelting processes emit SO2, and SO2 is really quickly oxidized to become a reflective particle. So it has this strange feature where it's associated with greenhouse gas emission, but it actually leads to a cooling because it's reflecting sunlight away from Earth. And so we've actually seen in 2020, we, as a kind of global community, reduced sulfur in shipping emissions, which actually reduced SO2 emissions, reduced this kind of reflective layer, and led to a bit of a temperature increase. And so the temperature profile that you get, especially the regional climate impacts, are very dependent on the emissions profile that you feed a model. And there's a lot of debate around that. Now, that said, I was kind of looking at the UKCP 18 report. This is from 2018, so it's a bit outdated now. Um, the general findings have remained. The UK projects greater chance for hotter, drier summers, warmer, wetter winters, and more extreme weather under this kind of high emissions scenario. And it's saying by 2070, winters could be up to 3.4 Celsius warmer and summers could be up to 5.1 Celsius hotter. Um, what I'm most struck by is this concept of how much more variable the jet could get, meaning how much more variable weather could get. I think since I think the last 2 years during the LA wildfires, there was a paper release that talked about climate whiplash and how extreme events on their own are very damaging. But if you have extreme events back to back, like a drought followed by extreme precipitation, then you actually get this kind of exponentially more damaging outcome because the land, in this example, if you have a drought, your soil is now hydrophobic. You have less absorption of what will be catastrophic flooding. Um, and you're more likely to have these oscillations between extremes, which themselves make each extreme more damaging. Um, that's not very positive a note to kind of leave us off on, but it is kind of how I think a lot of climate scientists are starting to think about um, assessment of extreme events is assessment not only of the frequency of the extreme, but also how likely it is to be occurring in tandem with another extreme event. Um, anyway, I hope that wasn't like a fire hose. I hope that people got something out of that, and I'm really happy to talk about anything.
We've got a question in the chat that
Oh,
says,
yes.
yes, yesterday's Guardian carried an article saying Atlantic, the AMOC, is significantly more likely to collapse than we thought before. Do you want to talk about the AMOC,
I can
Colleen?
talk about the AMOC. I did. So I think there is robust evidence that that's the Atlantic meridional overturning circulation, and that is the oceanic kind of circulation pattern that carries energy um, it- northward. And it kind of the AMOC is setting a lot of, I guess it's complicated. It's an ocean circulation pattern, but it basically brings warm air northward. And it brings heat northward in a way that specifically for the UK keeps you from being quite cold. Um, for example, I think what latitude you're kind of equivalent to parts of northern Canada, which is substantially more cold, but because you are carrying this warmer, moist air, um, AMOC has a lot to do with setting the circulation patterns, etc. There's robust agreement that the AMOC will slow down. I know the climate community is still relatively, I guess I went to a workshop recently where it was kind of the aerosol community, which is where I am, interacting with the tipping points community. And I didn't really realize that the tipping points community still feels like quite controversial because there's a lot of discussion around the term tipping and a tipping element. When people talk about collapse of the AMOC, that makes it sound like it would be incredibly sudden. And on geologic timescales, it would be sudden, but these things move slowly. So when I was talking to someone who studies the Atlantic meridional overturning circulation, they were saying that if you had a collapse, that collapse would take place over potentially like a 100 to 300 year time scale. It wouldn't be one day to the next. That's not to say it wouldn't be damaging, and it would absolutely change the entire Earth system, climate system. But I would say some of these articles that are scary, they are scary, and there is a chance of this slowing down, which would modify climate. But I also think the term tipping might be a bit misleading. Um, I know a lot of contemporary climate models, and this is partly because we don't understand the mechanisms or the dynamics that control tipping. But a lot of climate models actually, you can push them, meaning you can impose more and more greenhouse gas, and it's really hard to get them to tip. And so people are really working on understanding, well, A, is that real? Is that a real representation of tipping, or is that because we're missing something in our models? And it's likely that we're missing some key pieces of information that help us understand the mechanisms. Um, or B, is it because tipping is a low likelihood event? But even if it's a low likelihood but high risk event, it's still important to understand. So I would say, and I'm going to read on, I'm part of a group working to wake up our politicians. The AMOC threat is real. And I do think, especially the UK and Northern Europe, is at higher risk, I would say, than most other places because of how rapidly or how different the climate would be here if it does tip. The housing here, the infrastructure, I do not think is ready to be like Northern Canada. I mean, I've not lived here long, but my heating doesn't work. So I think that means that people are at risk of exposure. You just aren't ready. And so I do think any advice on suggestions to help our policy advocacy be effective. I mean, I wonder if it could be effective if you're able to talk to the AMOC people. the climate scientist studying AMOC, and I'd be happy to put you in touch to really, I think if you can go to a policymaker with the strength of understanding and data, I think that can convince them because I think, I think Tim Lenton in Exeter is the gentleman who's really known for understanding tipping, and he wrote the tipping points report. Um, was incredibly compelling to listen to, even though he was citing the uncertainty, he was still outlining how to approach change and how to really focus on this. So uh, I don't know. But then again, to be fair, I haven't done a ton of policy advocacy because I struggle to understand what policymakers are doing, um, which lends me to not be very patient. So,
Colleen, may I ask you to stop screen sharing so we can see
oh
more of your
yeah,
face?
there we go.
That's brilliant. Thanks so much. Um, uh, I think where Dave's coming from is the fact that we've got something called the National Emergency Briefing going the rounds. That was an event that was held in Westminster last November, and there's now a film made from that called the People's Emergency Briefing. Have you come across any of this?
No, and I'm writing it down right now.
Well, I'll send you the email and links and everything. Um, uh, but essentially, Tim Benton was one of 10 people who were giving a 8 to 10 minute talk to an assembled audience of very senior people. MPs were invited and leaders of industry were invited, but not every MP turned up. So what's happening now is that the film of the event with some audience feedback. So we've got some comedians who are giving feedback in the film to a thing that they've just seen in order to translate it into something that lay people might understand. And I've watched the film, and the feedback is of the nature of, oh my goodness, but
Yeah.
with expletives. And I think what we don't know as a climate group is we're all recycling. We're all, I mean, Martin's encouraging us to eat less meat, but we're all doing our kind of personal stuff, and it seems to be very ineffective. And if we look back from the last decade or so, from Greta Thunberg starting school strikes and Extinction Rebellion uh, raising attention, I think the sum total of that has been zero. There's no impact on our policymakers at all. Our house building standards have not changed in 30 years. They're getting slightly better insulated, but they're still incapable of surviving the minus 40 centigrade that if the AMOC did stop, we would be faced with. But I think we'll be starving by then anyway, so being the cold in winter wouldn't really matter very much. Um, uh, how much computing power does your model need? I mean, are scientists being constrained by the lack of computing power?
I mean, I think the research community, like the academic research community, has, apart from the kind of major universities, which I have had the privilege of being part of, it is quite, you're often trying to work on a shoestring budget, but I think that also makes people quite creative in their solutions. And I think it yields maybe a more conservative use of compute power, which I think is a good thing. Um, but to be fair, I mean, I think the UK, the US, there are these massive supercomputers, and so I don't think we're constrained by compute within reason. We're constrained by how complex your system is and how complicated it is to represent it. Um, and so I do think making compute available to not just the most rich institutions is more of a kind of almost like climate justice perspective, where I think um, if you can make it available to people with different backgrounds, then they'll look at different impacts that are more relevant to different areas and different demographics. And that's really important to try and include. And I know I'm sure the UK has a similar thing, but the US makes the kind of National Center for Atmospheric Research compute cluster available to anyone who can put in a short application, and they'll allocate you some amount of compute. My understanding is that the UK system, just called Archer, um, is a little bit more run down. Not run down. I think it's a bit smaller. It is a bit harder to get on, and I think there's a lot of more people going for the same amount of resources. Um, but that said, I think the UK government is trying to invest in compute, potentially not for climate science, but because AI and machine learning are coming up so fast. So I think while I'm not sure my ethical thoughts on AI and ML, I do appreciate that it could potentially unblock some barriers in understanding, climate science and being able to run these big climate models more efficiently. Um, I think, and I
Mike,
don't know.
sorry, I was going to say Mike's got a question, and I don't want to push you, but we've only got about 4 minutes left. Sorry,
Oh
Mike,
gosh,
do
yeah,
you
no,
want
go
to?
ahead. Also, sorry, I didn't see the hand.
Yeah, it's all very interesting. I really wish that I'd told one of my friends about your um, talk tonight because he would have been very interested indeed.
There will be a
he's-
recording and the slides will be available.
oh,
So,
yes, yes, yeah,
yes.
yeah. I mean, he used to, before he retired, he worked in the marine environment. And he's not particularly fond of these models because he used to take measurements of the deep sea and bring up the readings, and everyone would say, "Oh, we didn't expect that." Right, we'll go and make a few adjustments to the model. And nevertheless, this is always what happened. As far as the AMOC is concerned, I think the main risk to us in Britain at the moment is possibly failure of the subarctic Atlantic gyro system. That could bring a little ice age type of condition here quite quickly and knock back food production dramatically worldwide. But what my friend is interested in, he's done a little bit of research on CO2 from figures that are publicly available, CO2 emissions in the Arctic. And we noticed that during the first lockdown, and BP produced figures across the board of CO2 emissions based on the amount of fuel that the oil companies are releasing. And CO2 emissions during the first lockdown were predicted to have dropped. But CO2 in the atmosphere increased, as you would expect, because we're still adding CO2 to it. But the rate of increase also increased,
Oh,
which to us suggests that possibly we have crossed a tipping point. Of course, we're not cutting back dramatically to be able to test that, and it wouldn't be possible to do so. The other thing he's really interested in, I mean, we're all aware of the problems of clouds. This is a bit of a nightmare, but he's wondering how methane is dealt with in the upper atmosphere, because we've got lots of comments about how methane is operating in the troposphere. It behaves very differently in the stratosphere and the mesosphere.
yeah.
That doesn't seem to be being accounted for as far as we could see.
So in the stratosphere right now, the stratospheric methane is actually a source of water vapor because
Mm.
it gets chemically processed into water vapor, and then stratospheric water vapor ultimately, typically, I guess it is quite altitude dependent, but it has a surface warming effect. So it's got a local cooling effect because you're actually increasing radiative emission to space, but you're also increasing downwelling long wave radiation. Um, but so what most models do in the stratosphere is they have a simplified parameterization that basically just says, this is how much methane I have. I'm going to assume standard chemical processing, and I'm just going to directly compute it and say it turns into water vapor with this ratio. And what we're seeing is that as less and less realistic, especially as we've got increased growth in the space sector. So any sort of rocket launch is now
Mm.
um, inputting water vapor and methane into the stratosphere directly, and it's typically unaccounted for in a lot of these emissions trajectories. And so that's a major question in actually, are we going to anticipate more surface warming driven by this stratospheric input that is kind of not part of the typical surface emission scheme that we deal with? And that's also a question. I don't know if anyone's seen that there's a big investment recently into supersonic uh, jets, like the Concorde, to bring those back. And if even if you use kind of a more sustainable aviation fuel, you actually expect to input a lot more water vapor, such that even though it's not emitting CO2, it's still causing surface warming. So yeah, the stratosphere handles this chemistry quite differently, but it's still a problem, and it is very much an open question. And it's what actually I just got a grant to do that type of work for stratospheric modeling. So it's spot on that it's not really handled.
Good,
Colleen,
good.
I'm very aware that we've gone past 9 o'clock, and your colleagues at Churchill must be waiting for you down in the bar.
Oh,
Are you okay to carry on a little bit
oh,
longer?
I'm fine. Yeah, I'm. To be fair, I just got here. I don't know anyone. So if you have more questions, I have nowhere to be.
Well, that's such a shame because Churchill's such a lovely college. Anyway, Colleen's a by fellow at Churchill. Now, I have no idea what that means, but I think it means she doesn't get paid for being there. Is that right?
Well, so yeah, I'm a David Crichton Fellow in the Department of Mathematics, and then as part of that, I get a bi fellowship at Churchill. So they put me up. They're feeding me and housing me for the next several months. So
Okay. So, Rupert, you've got a question. Thank you for being patient.
oh,
Yes, fascinating talk, Colleen, but for political reasons, we need to keep things simple. Because people like the Reform Party will say these scientists don't know what they're talking about, they don't agree. And so we do nothing. And so we need to have something definite. And are there any changes that we need to make in our existing behavior? I mean, we're trying to cut our CO2, we're trying to cut our methane, we're trying to do this and trying to do the other. We don't need to change that, do we? That's the first question. And secondly, warfare is never mentioned. And with the war going on, that must be having a huge effect on the climate. I mean, it's blowing things up, things are being destroyed, they've got to be rebuilt. There's a colossal input of CO2 and consumption of resources going to be necessary. I don't expect you to be able to answer these things, except that are we doing the right thing apart from fighting each other at the moment?
I guess I'll comment. I know I was looking, there's a paper recently that was estimating the CO2 emissions that will result or have resulted from the war in Gaza thus far. Obviously, this kind of Iranian conflict, I don't think a paper is out about that yet, but it certainly does. War itself yields uh, massive emissions injection, um, which makes sense.
And the military never get accused of, never have to give
No,
any
their
estimate of
emissions
it, do they?
output. They don't. Additionally, I know like the US military is not accounted for in CO2 emissions for the US, and I think that's consistent worldwide. And it will likely be one of the most, after kind of aviation, it's going to be one of the most difficult sectors to decarbonize because, gas and oil, there is infrastructure, it is quite reliable, flexible. So that is actually a big point of discussion in kind of the geopolitical climate science community. Now, as far as things that I'm going to say broadly, like our governments should be doing, it is cutting emissions is the number one thing. Decarbonizing our economies, our infrastructure, reducing CO2 output is number one. I know a lot of strategies cited that for the near term, cutting methane because it's a strong short-term climate forcer, was a focus. And hypothetically, that was and is true, but I think they said that because that is the easier thing to approach. Cutting down your methane emissions is a lot easier than redoing the infrastructure that enables kind of CO2 emission. Um, I just think, yeah, and I'm also in the meantime reading this comment saying it is derailing and distracting, I think, from the climate movement. And I think that's true of a lot. I mean, this is me. I listen to a lot of books on tape, and I think one of the things that I've really come away with is when there are, wars. I know in the US right now, like inflation, instead of being worried about climate, you're worried about your housing, your groceries, the ability to like exist. I mean, I'm 33. I was hoping to have a family. I'm quite worried about affording all of this. So it does distract from being able to be worried about climate on a day to day, and it sucks your energy out of you. I do think that's a big worry. And I think we did see that the climate movement and the momentum that felt like was happening was kind of deflated with COVID. I thought there was actually some traction, and I thought people were starting to really care, and politicians were taking notice, and then it really kind of got derailed. Um, so how to get us back on the rails is a big question. Um, I do, for better or for worse, I actually think people realizing how dependent they are on foreign oil and fuels coming from the blockade, um, I think is helping the argument to move to renewables and this concept of energy kind of independence. It is a question of what direction a government takes that in. Is it, oh, I'm only going to, go into Venezuela and steal my oil and have it all for myself, or is it I'm going to invest in renewables? So it depends, but I do think people advocating at the local and national levels to their government is the best we can do. Um, as a climate scientist, I also struggle, I'm contributing to the IPCC report, but it doesn't really feel important. At some point, we've already said what's happening. So saying it again and again and again and expecting a different response feels a bit, I don't know, it's
So,
futile.
so that's why this film is so important, because the idea is to get it across to people who are not really thinking, leaders who are not thinking climate, and just get across to them, this is urgent, we need to do something about it.
Yeah.
And they haven't got it, a lot of them.
And I just don't, yeah, to me, it's just incredible because it impacts everything else, right? Like maybe the climate doesn't seem like the forefront thing, but it will layer upon any other issue in any system. Um, and that's historically known. There's a great book called El Nino and the Collapse of Civilizations. But it talks about how climate can often be the kind of the straw that breaks the camel's back when there's other, issues with societies and resources. And this climate is the final thing that kind of can break down societal structures. And that really changed my perspective. Anyway,
Mm.
so, but no, I come to you also not having solutions, but hopefully finding community with like-minded people is really quite nice. So, and having a space for advocacy. Yeah.
I feel hugely privileged to have had you here this evening, Colleen. Thank you so much.
Yeah, no, really fascinating talk. Thank you. Yeah,
Very, very good.
really good.
Mm.
Oh, thank you
Yes,
so
thank
much.
you.
I was so happy to be here. So, and I can send you my slides, and if anyone has questions,
Perfect. Thank you.
Certainly feel free to stay in touch.
And I have to tell you, in Cambridge, they punt from the wrong end. So don't go punting. If you do go punting, you'll find that in Oxford, they stand on the deck, on the bottom of the boat. Whereas
Rubbish, Harry. Cambridge have all got it absolutely right. And these Oxford people haven't a clue what they're doing.
they stand on the deck. How ridiculous is that?
I think Harry and Rupert need to have a boat race.
How long are you in Cambridge, Colleen?
I'm here until the 1st of July.
Okay, so can we meet up and go punting?
Oh, of course.
Rupert, you up for that?
Good
I
idea.
can't wait to see who falls in the river first.
As long as you've had your jabs, it doesn't matter. So
I'll
If
stand on
anyone's
the
up for
bridge.
a
I'll
trip to
stand on the
Cambridge,
bridge and grab Harry's punting pole as he goes.
I'm with you, Harry. We can't
Leave him
go
hanging
off.
there.
Yeah.
excellent, Colleen. Thank you so much indeed, and thank you
thank
everybody
you.
else for joining
Thank you.
us.
Yeah, thank you so much. And I'll
Can I
send you
just
all
have-
my slides.
Sorry,
Thank you.
Jane,
So
you've
just
got
a
some-
second, 30 seconds just to say that the next month's meeting is on the 21st of May, and our speaker will be Stuart Dawkes, who is the CEO of an organisation called PECT. Originally, that stands for Peterborough Environment City Trust, who do lots of things about protecting and enhancing the environment in Peterborough. They do projects around energy, nature, waste, food. So I think that should be a really interesting talk. A completely different perspective, but I think it needs to be everything everywhere all at once. And I was just thinking when you were talking about the methane thing, it's all very well, yeah, great, focus on methane, but it isn't a binary thing, is it? You've got to do methane and carbon dioxide and everything else.
Yeah, but to kind of come at the issue all at once, it's
Yes.
hard to actually
Yeah.
make it. Oh, but no, this is lovely. I really appreciate this group. So thank you
Oh,
so
thank
much.
you. Yeah, no, we appreciate ourselves.